The discussion is on de Broglie's matter waves and an expression for a de Broglie wavelength. Before going to discuss this, the recap or recall the topic what we discussed in the previous class is Compton effect and an expression for Compton wavelength, special cases of Compton effect. When a monochromatic beam of X-ray is incident on solid like carbon atom, the beam gets scattered. The scattered radiation has a frequency which is less than the incident frequency in addition to the incident frequency. This is observed by Compton and the effect is called Compton effect. And using this Compton effect, we want to discuss about the expression for Compton wavelength by using the two conservation laws. One is called conservation of linear momentum as well as the conservation of energy. I take a short part of this. Let P1 and P2 be the momentum of the photon before and after collision. E1 and E2 be the energy of photon before and after collision. PE be the momentum of the electron. Then apply conservation linear momentum. P1 is equal to P2 plus PE, or PE is equal to P1 minus P2. Then you simplify this equation. And similarly apply the conservation of energy. Another equation comes into picture and equate these two equations. The final equation of Compton effect is d lambda is equal to h by m naught c into 1 minus cos theta. Then here d lambda be the change in the Compton wavelength, h is that is called Compton shift, h be the Planck's constant, m naught mass, the rest mass or dynamic mass here in this case, c with the speed of light. Now come to the special cases. When theta is equal to 0, cos theta is 1, d lambda is equal to 0. That means lambda dash minus lambda is equal to 0. Lambda dash is equal to lambda. The wavelength of the scattered radiation is equal to wavelength of the incident radiation. That means there is no change in the wavelength. That is called coherent scattering process. Second one, if theta is 90 degree, we get the expression for Compton wavelength. D lambda is equal to h by m naught c. Similarly, special case 3, when theta is equal to 180 degree, d lambda is equal to 2 into h by m naught c. Substitute the value. The answer is 0.0484 angstrom in it. The de Broglie's hypothesis of matter waves, inspired by the dualism of radiation, de Broglie proposed his hypothesis of matter waves based on the following consideration. The whole energy in the universe is in the form of matter and electromagnetic radiation. The second one, nature loves symmetry. Hence, wave particle dualism which applies to the radiation must apply to the electron and other particles. The de Broglie, by consider this idea is, he consider the phenomena like interference, diffraction, polarization, etc. are explained by considering light is a wave. Similarly, the phenomena like Compton effect, photoelectric effect, Raman effect, etc. are explained by considering light is a particle. But light explains all the phenomena. It explains interference, it explains diffraction, photoelectric effect, Raman effect, etc. That means light shows both the nature called dual nature, that is called dual nature of light. Louis de Broglie applied this property to the other than light like electrons, protons, etc. Surprisingly, these particles are also shows wave nature as well as particle nature called dual nature of matter. The waves associated with the moving particles are called matter waves. Wavelength of the wave is called de Broglie wavelength. Our wavelength associated with the matter wave is called de Broglie wavelength. Now, we want to derive expression for a de Broglie wavelength. According to de Broglie, associated a wave with every moving particle, and these waves are called matter waves. That means a simple way of expressing what are matter waves. Waves associated with moving particles. According to quantum theory of radiation, the energy of photon is given by E is equal to h nu, where h is Planck's constant, nu be the frequency of radiation. Then, using Einstein's mass energy relation, using Einstein's relativistic energy equation, E is equal to square root of m naught square c square plus p square c square Here m naught be the rest mass of photon, p be the momentum. A photon, its rest mass is equal to 0. When the rest mass of the photon is 0, m naught is equal to 0, then E is equal to square root of p square c square, or pc is equal to h nu. Simplify this equation, then lambda is equal to h by p is the expression for de Broglie wavelength. De Broglie wavelength is also expressed in other two formats. One, we know lambda is equal to h by p, where p is the momentum and p is expressed as p is equal to m into v. If Ek be the kinetic energy of the electron, then the expression for kinetic energy is Ek is equal to half m square. 2 cross multiply, mv square is equal to 2 Ek. You multiply left hand side by m and right hand side by m, then the equation becomes m square v square is equal to 2m Ek. mv is equal to square root of 2m Ek, or lambda is equal to h by square root of 2m Ek. Then another form of expressing de Broglie wavelength is lambda is equal to h by square root of 2m Ek. Also we know the energy, kinetic energy E is equal to E into V. Then lambda is equal to h by square root of 2m Ek. Instead of Ek we put to E into V, then lambda is equal to h by square root of 2m EV. So there are three ways of expressing de Broglie wavelength. First one, lambda is equal to h by momentum, that is lambda is equal to h by p, or lambda is equal to h by mv. Second equation of de Broglie wavelength is lambda is equal to h by square root of 2m Ek, where Ek be the kinetic energy. And another equation is lambda is equal to h by square root of 2m EV. V be the voltage or potential difference, E be the electronic charge, m be the mass of an electron, h be the Planck's constant. If we simplify this, the lambda is equal to 12.27 angstrom divided by root V.